Today, we're going to talk about a ghost. And no, not the kind you're thinking of. This one is way more dangerous, and it haunts the very code that our modern world runs on. I mean, think about it. What if the machine that's supposed to save your life tries to kill you instead? It sounds like something out of a sci-fi movie, right? But for a handful of patients back in the 80s, this wasn't a movie. It was a horrifying reality. This is the story of how a tiny software bug turned a healing machine into a lethal weapon.
All right, so let's set the scene here. The machine was the Theric 25. At the time, it was this cutting-edge medical accelerator designed to treat cancer. But something went horribly wrong. Instead of healing people, it started zapping them with radiation doses hundreds of times stronger than intended. The results were, well, they were catastrophic.
And you gotta understand, this wasn't some silent, invisible error. The patients felt it immediately. One patient in Texas, Ray Cox, said it felt like a massive electric shock. It was so bad he literally screamed and fled the room. And others reported similar, terrifying experiences. But here's the crazy part. At first, nobody believed the machine could be the problem. So, what was going on? It all came down to this one crucial design change. You see, earlier models had physical mechanical safety locks. Think of them like a deadbolt on a door, a real physical thing that stops something bad from happening. With the Therac 25, they got rid of those. They decided to rely almost completely on software to do the same job. And that single decision set the stage for disaster. After months and months of investigation, the truth finally started to come out. The hardware, the physical machine, was fine. The problem was hidden. It was a ghost in the code, a flaw buried so deep in the software's logic that it would only appear under a very specific and very tragic set of circumstances. Okay, so what was this ghost in the code? To really pinpoint the culprit, we need to dive into a specific kind of software flaw, something known in computer science as a race condition. The name sounds pretty dramatic, right? But it's actually a perfect description. Imagine you and a friend are trying to flip the same light switch at the exact same time. Whether the light ends up on or off depends entirely on whose hand gets there just a fraction of a second faster. Now, for a light switch, who cares? But when you have two parts of a program racing to change a critical piece of information, that unpredictability can become incredibly dangerous. And this is exactly what was happening, and it was so specific. An experienced operator who knew the machine well would type in the treatment settings. They'd notice a typo, and really quickly, we're talking within 8 seconds, they'd use the arrow keys to go back and fix it. Now, on the screen, everything looked perfect. It showed the corrected low-power mode. But behind the scenes, the software was lagging. It updated the screen, but it didn't have enough time to move the physical safety shield into place, so the machine fired the high-intensity beam with no shield directly at the patient. This specific kind of race condition actually has a formal name: time of check to time of use, or TOCTO for short. It's like looking both ways before you cross the street. You check and the coast is clear. But in that tiny gap between your check and when you actually use that information to step off the curb, a car comes speeding around the corner. The situation has changed, and your initial safety check is suddenly useless. We see this exact problem used in cybersecurity all the time. It's a classic attack. A program checks, hey, am I allowed to write to this harmless little file? The system says, sure, go for it. But in the nanosecond after that check, an attacker pulls a switcheroo. They swap the harmless file with a link to something critical, like the system password file. The program, thinking everything's fine, goes ahead and writes, and bam, it's just corrupted the whole system. Same principle, different context. So this really just lays it all out, side by side. The old way used physical hardware locks, totally independent of the software's timing. The new way used software checks, which were completely vulnerable to these tricky timing bugs. They traded a physical certainty for a digital assumption. As you can see, this problem, managing the order and timing of events, is just fundamental to how computers work. And the Therac 25 is a brutal lesson in why getting it right is so critical. This brings us to a brilliant computer scientist and his groundbreaking solution. So here's the big puzzle he set out to solve. Imagine you have dozens, maybe thousands of computers all talking to each other. None of their internal clocks are perfectly in sync. They're all just a little bit different. If computer A sends a message and computer B sends another one, how can you possibly prove which one really happened first? It's a surprisingly tough problem.
Enter Leslie Lamport and his absolutely elegant solution, the Lamport timestamp. It's not a clock in the way we think of one. It doesn't care about hours and minutes. It's a logical clock. Really just a simple counter that lets a system create a guaranteed order of events based on cause and effect, instead of relying on real-world time.
And the algorithm is deceptively simple. It just follows 3 basic rules. First, every computer keeps its own counter and just ticks it up before it does anything. Second, when it sends a message, it includes its current counter value. And third, when a computer receives a message, it just adjusts its own counter to be higher than the one the message it just got. That's it. And this is the magic of it. A Lamport timestamp doesn't tell you that event A happened at 2:30 p.m., but what it does give you is mathematical proof of causality. It lets you say with absolute certainty that event A happened before event B. It establishes this unbreakable logical order of events.
Okay, so let's bring this into the modern world, because these ideas about timing and order are not just academic. In today's high-speed, high-stakes systems, they are absolutely everything. And there's no better example of this than in the world of finance.
Just get a load of this number. During the 2010 flash crash, high-frequency trading algorithms executed 27,000 trades in just 14 seconds. That is nearly 2,000 trades a second. At those speeds, a single microsecond, a millionth of a second, can be the difference between making millions and losing millions. And this is the kind of insane infrastructure it takes to win that race. To get that microsecond edge, trading firms use everything from GPS satellites in space to precisely synchronized atomic clocks located right next to the stock exchange servers. The race has moved from seconds to nanoseconds. So how do we prevent another Theriac 25 from happening? Well, today's programmers have a whole toolkit. They use things like locks to make sure only one process can touch a piece of data at a time. They use atomic operations that are guaranteed to happen all at once or not at all. They design entire systems to avoid sharing data in the first place. These are the modern defenses against the ghosts in the code. You know, the story of the Theriac 25 is such a stark reminder that software isn't abstract. It has real-world consequences. As our world becomes more and more dependent on incredibly complex, high-speed code for everything, from our cars to our medicine, the question remains, are our safety checks keeping pace with our ambition? It's a race we simply can't afford to lose.